should be making a video. Another draftphysics.com, debatephysics.com, also video presentation and such. Yeah. I'm here until I'm not here. So I'm already tired, I think, or something. Tense, unsettled. So, so this guy, Rhett, what's that his name? I don't remember. Allain, something like that. Anyway, I must have run across his videos a couple of years ago because I saw a couple that I recognized. And but I don't remember doing exactly these videos in terms of making responses. And, can't hurt. And, I did send him an email. I didn't get a response yet, but we'll see what happens. Whether he wishes to, in some way or other, participate in this 400-year-old, I would argue, completely unresolved argument about the nature of energy. And you could argue that the whole argument about photons got ruined around the same time, with Huygens versus Newton, and somehow, once Newton was dead, the Huygens-esque theory of a non-corpuscular photon waving through space, became the dominant perception. Even when they realized that there were pretty strong pieces of evidence saying it's not a wave. Richard Feynman even overtly says it in one of the Feynman lectures, that he wishes they didn't teach it that way. It's not a wave. It comes in clumps. The detector doesn't work that way. He uses lots of statements saying that kind of overtly. And yet everybody says, no, it's a wave in some kind of medium. That they won't describe or define as anything except some vague notion of some wobbling fields or something. Some kind of magnetic field causes a wobble in an electric field or whatever. They can't draw you a picture of it. That's the simple truth. All right, and I have gone over it and over it in terms of what I would argue is the simple answer is that there are bits of energy. And they all have a consistent, the same capacity to make something change or happen because they're all the same thing and they're going the speed of light. So it's a bit of sand or whatever you want to call it, some little tiny thing. It carries a momentum and they come at a frequency. And that simple explanation does work. Certainly is uncomplicated. So you can just understand the frequency is just the distance, at which they arrive, on a surface, and that timing is what defines them. So, if they're this far apart, they're red light. If they're this far apart, they would be blue light. It'd be that simple. And then you have to add the little bit of extra is when they land on a surface, and we're going to land on a surface based on their frequency and wavelength is going to decide effectively how big they are, how fine the resolution is, and that just has to do with how big the amount of surface you need to hit to have what's called a photon. So the simple argument is Feynman diagrams are nonsense because Feynman diagrams basically say, a photon can just pop out of one atom. So somehow an electron moves and a photon pops out. And no, this pops out. One thing, pops out. One part of a photon. So anyway, the simple fix for polarization is just to realize that, especially antenna polarization, when you're putting electricity into a wire, it takes time to get up through the wire. And the fact is this bit will be excited first, and then this one will be excited later, and then later. And so the sending of message, the message will be separated in time and also separated in space. And so this will be the polarization, and this will be the frequency, and they will be proportional to each other. And it can be understood that way. So they just fly parallel, and that simple explanation does work. So it's viable. It's not, no one's really going to provide you any logic that says it can't be, can't happen that way. They're not going to show you the can't happen experiment, can't be experiment. They're not going. It's not going to happen. They're just going to claim it has to be what they claim it to be, which is it has to be a wave of some kind. All right, so we'll play some of the video, and then we'll see if I need to draw further. But it's going to get into the double slit too, very briefly. But they're really not going to talk about it. They're just going to say it means it's a wave, when obviously if you really analyze the experiment, it doesn't mean it's a wave.
So we have a lot of demos that we can.
All right, so this is very bad quality audio, so I'm going to have to do something to fix that. It's got some background noise in this one to start with.
Do with light. Here's one. This is just a lens, and I have a little screen here, and I can move this up, and I can focus. Let's see if I can get this right there. There's a light that I'm focusing right over there. It's the light's way over there. So it's classic example of light is a wave. We understand this.
So again, I don't even understand this classic example of light as a wave. When if you do the math, it's all vectors, straight line vectors. The bending's all straight line vectors, nothing waving. It's all rays and hitting locations on the lens. The lens actually is shaped, the surface, and it bends light more on the outside and bends less on the inside, and it's made of a bunch of rays. So I don't know how that experiment demonstrates anything to do with waving.
We even have things like this. Here is a laser pointer. You can see that little green dot. You see right there, it's not super bright.
Yeah, no, you really can't see it.
And if I put this diffraction grating in front of it,
you won't see any of that.
Then
either.
I get...
So this is just more than one slit. So the more slits you add, the rounder, the more perfect the image of the laser gets, and the further away they get in space. And so again, all you're doing is sending, again, straight line vector math predicts every bit of this. And wave mechanics, you'd say, what are you talking about? Okay, because it's really just about the surfaces of whatever it is you're shooting the light next to. If it hits a surface, it's from that surface. It's not some bulge that comes through the opening. So the opening between the surfaces doesn't have anything to do with it. It's the surfaces that have everything to do with it.
3 dots. Again, we understand that.
Okay, so whatever. Again, we understand it, meaning we sell a theory and we don't bother even mentioning any other theory. We don't even describe one. We don't even challenge our own beliefs by saying what if. We don't even do anything to change whatever, the religious statement of waviness that isn't there.
Now we have something like this. This is a little homemade electroscope I made when it gets electrically charged.
Yeah, so this is really a bad example because it didn't work very well, but whatever.
Things spread out, so let me charge this thing up. I'm going to charge it up this way. I have a little, this is just to make it easier, and I'm holding on to it to make it negatively charged. Okay, I think that's good enough. Let me do it. And now here I have an ultraviolet light that is not on. And watch this thing right here.
Yeah, it barely moves. So it wasn't a great demonstration.
Notice how it's decreasing slightly right here. Okay, this is the photo.
So the idea is that he's put extra electrons on it. Okay, and now he's going to knock them off with the ultraviolet light. And obviously, yes, it's easy to knock electrons off the surface of atoms. So extra electrons are detached easily, and then the more attached electrons are a lot harder to remove. But anyway, it does work. And it also works to create electricity.
Electric effect. It's not the best version of it, but I can get a better one. This one's kind of harder to explain using light as a wave. So this idea, well, maybe light's not a wave, maybe light's a particle. So what is it? Is light?
Right. So he's conceding that there are experiments that demonstrate that the wave theory is, you know, not that solid. That there's are reasons to say really can't be a wave. This doesn't make any sense. There's no analog to the wave. There's no, the wave is strong, the wave is a little weaker, it's a little weaker, it's a clump. A clump has to knock that electron off, a clump of energy.
Wave or particle, or is it both? Or does it get to decide? That's what we want to talk about. Okay.
Okay, so at least he's back in the office, so that's good.
So I have here some physics textbooks. Let's just see what they say about the nature of light. Okay, so 1886, 1887, experiments, Maxwell's equations, our wave. Theory of classical electromagnetic waves. Cool. Hertz. Then we get down to photoelectric effect. Planck's constant, blah, blah, blah. In 1905, same year, he published his theory of relativity. Einstein explained that the photoelectric effect and correctly...
So again, there's two types of photoelectric effect. There's the one where you just create electricity because you're pushing, okay, electrons from atom to atom, essentially. And then there's the case where you hit it with enough energy to ionize, that is, eject electrons.
Predict the results of some new experiments. Einstein said that E&M radiation itself is quantized.
Right, so instead of saying the photon is made out of quantized clumps at a frequency, which is one way to quantize, the sensible way to quantize, it's been interpreted as saying the photon itself is a quantum. Now, I'm not sure that's what Einstein intended people to think. So, you know, it's always a problem that, you know, things aren't written in English and then they get interpreted and, you know, who knows.
The quantum of E&M radiation, the smallest indivisible unit, is called the photon.
Right, so I'm not sure that Einstein called it a photon. And I think all he was saying is that the idea of what we would call light energy, or what was called light energy before the word photon, was that it's just made out of quanta. So that's simple a description. So again, the word photon wasn't in use. So it's kind of silly to say Einstein said it's a photon. He didn't.
So
he didn't in any sense other than he used somebody else's definition of a photon.
The key to understanding the photoelectric effect, blah, blah, blah. Okay. So, but it doesn't say what is it.
I wonder if it gives the accurate title of Einstein's paper, because I don't even know if it said photoelectric effect. That's us afterwards describing it.
The smallest indivisible unit called the photon. Okay. That's a physics book. This is an introductory astronomy book. According to wave model, blah, 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 electromagnetic wave or electromagnetic radiation. Okay.
Right, and exactly how does this wave model work in the sense that you can't make a laser beam out of waves. So we can't do that. We can't create a wave mechanism that can wave through a medium in a straight line. So what are we talking about here? Where's the physical example that you're going to use for an analogy to this wave idea? There's no physics that demonstrate it, that parallel it. So why is it popular? You know, because it's wrong. Okay, I saw a video talking about electrons and how they spin. Yeah, well, you can see a video talking about it. That's I saw one with the Arvin Ash or whatever the hell his name is, Ashy Arvin or some kind of guy, and it's just yeah. I mean, it's a video I'll have to play in the future because yeah, it's just such bullshit. You know, they start talking about this electron spin shit. You know, that somehow an electron is a dipole. The whole thing is so idiotic. You know, this fundamental charge is somehow a dipole. It's somehow a magnet. No, it isn't. Oh, it's just disgusting. The explanation for electron spins is described as spinning, but not really, that it doesn't seem connected to reality. Yeah, it's not spinning, but it's spinning. Yeah, again, and there's all just based on this silly notion that they're saying every time an electron moves, it's somehow creating a magnetic field. When, no, what it's doing is moving relative to protons in the nucleus. So every time you move an electron, obviously you're changing the relationship between the positive and the negative charge. So you're creating a change in the magnetic field that already existed. The electron is not creating a magnetic field, it's just changing the magnetic field. And obviously a changing magnetic field is what creates a phenomenon, not a stagnant magnetic field. Stagnant magnetic fields become neutral and nothing because they change something and that's it, they're done. But changing magnetic fields keep things jiggling all over the place. So that's the difference. Is that the electron is not a dipole. It's just so silly. I mean, it's silly. Fuck, I don't, when is this, this physics is so wrong. It's so exaggerated and it's so, it's just plain wrong to say the simple answer isn't the right answer, that the electron is a negative charge. Obviously, when it moves relative to a positive charge, that's going to mean that dipole is essentially rotated. And you rotate a magnet, you rotate the magnetic field. What? Duh. Just fucking duh. I shouldn't have to explain this to these college graduates. I mean, it's just so fucking stupid.
The wave model of light works well to explain many phenomena, but it fails to explain some of light's properties when it interacts with matter.
Like all of the properties when it interacts with matter. Like in every single way, it doesn't make any sense. You blow smoke on a laser beam, it almost couldn't look more like clumps of sand or anything else, and you stuck little mirrors in there and the sand bounced off the mirrors and hit your eye. I mean, you can't make it any clearer. That's basically all you're doing. You have a density of material, it's shooting in a beam, and you're going to create some little kind of stuff for the beam to crash into, and little bits of it are going to fly in all kinds of places, and you're going to be able to see the beam. But obviously the beam is losing some of its energy to hitting that smoke or that vapor or whatever you're using to see it. I mean, it's just so obviously not waving. I mean, what about a laser beam and, blowing smoke and watching laser beams shoot through it? What about that looks like a wave? I mean, I can't believe you have the argument because it's just saying, where does this look like a wave?
In those circumstances, it makes more sense to use a model in which light is thought of as a stream of particles.
There you go. So that is the sensible argument, right? And I think that's the argument Einstein was trying to get to. A stream of particles, and you need a certain amount of them, and they have to be at a precise frequency to be a photon. If they're not at the right frequency, if they're out of phase or something else happens, it won't work. It only works if it hits the surface in the right sequence to cause the motion of electrons. And that's how we see a photon, is we see the matter react to the energy hitting at the right sequence, and it causes our, inside of us, it causes electrons to move on surfaces. And it's the movement of the electrons that we're calling a photon. I mean, this physics isn't that deep and that abstract. It's not that hard to see the truth.
Called photons. The photons are individual packets of energy moving through space in a straight line.
So the photons aren't. The elements of the photon are. So a photon is an object. It's made of, let's say, 3 bits. That would, the minimum would be 2, right? You can't have a frequency unless you have at least 2. So obviously I would say 3 could be the number necessary to give the electron enough momentum to push into the next electron and cause a cascade. So you're just talking about you want to correct enough velocity in the electron that the electron doesn't move other electrons. It only moves the one in front of it. So let me draw that, because that's a really important concept to understand, that things completely change with velocity. If you can get an electron to go fast, it's completely different in how it interacts with the system of the atoms. All right, so, if you have a system, all right, we'll use X's for nucleuses. All right, so this is your surface. You have some electrons on this surface. And the idea is when you punch into this electron, let's say, it's going to push on the atom. And so the electrons here and here and here and here, you can understand that those electrons will push. They'll get some momentum because the pressure can't get increased this way because this is where it's more and more dense. So it has to go this way, just like water waves have to go up because it's the only place that's lower pressure. Well, the same thing's going to happen here. And the same kind of effect is going to happen. Okay, so, and what you're really saying is what you want is for this to be fast enough, this motion of this electron to eventually be fast enough that all it moves is this electron into this electron into this electron, just keeps squishing the atom, and nothing else is stealing the energy, essentially. So in a way, you want it to be almost as if these electrons were doing the moving. All right. But, I don't see practically how that can happen. So they can only go in and out. All right. And these are the ones that can go in a direction. And so the simple truth, though, is the faster they're going, you can understand if there was two electrons binding something in a system, and you were going to push another electron through, the faster I make this electron go through, the less it pushes on these two. So you understand that? The faster it goes through, just like with gravity, the faster I go through a gravitational field, the less gravity affects me. Same thing's going to happen here. This force, these things can only feel each other at the speed of light. And so if this thing moves fast enough, there won't be enough time for there to be a reaction here, and you won't push on this electron and push on this electron. You'll just scoot right through. So if I actually made this system, where I had put two magnets, and then I shot a third magnet right through, the idea is that if I shoot it slowly, then these two will get pushed. But if I shoot it really fast, those two will stay right there. And that's the idea of sound propagation. That's what you want to do in sound propagation. You want to create a fast enough motion that you don't move all of the other atmosphere. All the other atoms don't get jiggled. You just want to move a row of atoms. You want to go bang, bang, bang right through them all. And the same thing is true here. Is the faster you can get that electron to go, the more it conserves its energy, and that's what you want because that's electricity, right? Electricity keeps going down the wire. It's not losing its energy. And so that's the idea. That's how you move electricity, is to create a voltage, is to create enough pressure so when it pushes fast. And so it's so fast that the other electrons don't do any of this. They don't get moved. That's the simple argument I'm trying to make, is the faster they can go, the faster you create that change, the less the rest of the system will feel it. And the slower the change is, the more the rest of the system will damp all of the energy out. So you can't make voltage without a minimum amount of pressure, and that's essentially what the photoelectric is demonstrating. The photoelectric effect is basically saying if you don't hit me with a quick enough frequency, the system, okay, you won't get enough velocity. It'll get sucked out of the system. You won't get it up to speed fast enough. You need to get the electron moving fast. And the way to get it to move fast is to have these three things hit it quickly. The quicker these three things hit into the system, the faster that electron moves, and the faster it moves. The faster it moves faster, the quicker it gets up to its quicker speed. Yeah, I think that's an adequate explanation.
At the speed of light. It's another physics book.
Speed of force.
We've seen in chapter 24 that light
What
is...
happened? Where's the volume? I didn't touch anything. I really didn't. I guess it was something quirk with his video.
Electromagnetic wave. However, we must discuss the surprising fact that visible light and other types of electromagnetic waves are composed of discrete particle-like entities called photons.
So the real thing is the force tons, if you want to call them that. Some other word for the idea that the photon is the composite object. A photon is not a blob. There's not a 10-mile long blob flying through space with a radio wave. No, there's a little tiny discrete bit of energy moving the speed of light, and then 10 miles away there's another one, and then 10 miles ahead of that there's another one. That's the frequency. All right, and that's what's hitting the antenna, is that sequence of events. So it's an event. Photons are an event that hits a surface. They're not an object hitting a surface. And I think that's really easy to... I don't think there's any more reasonable conclusion that can be drawn if you pay any attention to the evidence that exists. It is ridiculous to think of some 10-mile long snaking wavy thing. But realizing that discrete bits moving the speed of light could have a 10-mile difference between their location, perfectly reasonable. That's exactly how a cork gun could work, or any kind of device where you could shoot like a BB gun, 1 BB, 2 BBs, 3 BBs, and they would follow each other in space. Same exact thing.
Okay, so the question is light a wave or a particle?
It depends on the experiment that you set up to test it.
All right, so I don't know who that guy is, so maybe we should find out who these other people are. Maybe I can email them. Yes, since they did make a video, technically, and assert a point. Okay, but again, this is college teachers, and they're kind of like, I kind of like they were teaching 10-year-olds, frankly. I don't really get it, but that this is college physics.
What do we tell students about light, whether it's a wave or a particle? What do you think
So there's another guy's a teacher.
about that? Do you think light's a wave or a particle?
I think it's easier to explain as a wave. I think it's definitely a wave.
Okay.
All right. So what is that? Easier to explain as a wave, But how exactly could you explain it as a wave in all of optics, when every drawing you're going to do is going to show a vector, a straight line vector of no size going through the lens? I mean, it's a no-sized vector, ray, whatever you want to call it, going through the lens. It's going to be, and it's all going to be perfectly straight line vector math. There's nothing going to look like anything like a bend or a wave anywhere in it.
I mean, when you talk about diffraction, when you talk about the spatial extent of it, when you talk about how it interacts with materials, because it's frequency dependent.
Yeah, and more exactly, but it's multi-atom dependent. So that's the one that's so obvious. You can't hit a single atom with a photon. You can't see a single atom with a photon, because the photon is 500 atoms across. Okay, so how can something 500 times bigger than the atom hit an electron that's 1,000,000 times smaller than the atom? Oh, that would be really ridiculous, right? Yes. So obviously it can only be a piece of a photon interacts with an atom. The energy is absorbed by different atoms, and the composite effect is the photon. So the pieces of the photon hit the surface like bullets from a plane shooting people. Unfortunately, strafing. So the first bullet hits here, the second bullet hits here, the third bullet hits here, and the idea is the object is moving faster than the bullet was, so it's going faster, and then it gets hit behind again. It goes a little bit faster. Then you hit behind it again. It goes a little faster. That's sort of the idea. You're not hitting the same electron, but you're hitting behind the effect of the cascade of electrons. So if you want to call it a wave in the surface, in the sense that the electrons could look like a wave, like in a stadium, where people stand up and something, it could look like it, but the force isn't waving.
When you talk about the manner in which it, interference effects, So
So there's no such thing as interference. So that's just a wrong concept. And all you're really doing is you're breaking photons by having them interact with a surface. So the smaller I make an aperture, the more I guarantee that the photons go right by a surface and get broken. And then they all become fringe light. So if I want to spread the light the maximum amount, I make the hole smaller, 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 and I'll essentially spread every bit of it. Not a single photon will go straight through. So, you know, it's just so obvious this is a surface effect. You're just breaking photons. And the simple argument is, well, I got a 50-50 chance I put them back together in phase, out of phase. That's all there is. There is either they're towards going in phase or they're towards going out of phase. But that's the only two choices there are.
it's easy to conceptualize it as a wave. I think you have to be a
I
little.
think it's impossible to conceptualize a wave. I don't know how you do it. I don't know how you think about it. I don't know how you contrive that nonsense. There's absolutely nothing about it that seems wavy. I mean, nothing about it that seems wavy. The whole way you can, you know, just by making an aperture, you can reduce the amount that's going through an area. I mean, it's just so obvious that all the photons, a piece of them aren't going through my aperture. You know, it's obvious that there's only a certain number of particles or a density that goes through the aperture. There's no waving.
A little bit careful. The light doesn't care. Light doesn't care about whether it's a wave or whether it's a particle.
Oh, who cares? Like, duh. Okay, so no one's making the argument that photons care. So that seems like a bit of a straw man argument, right? That, oh, the opposing side thinks that the photons care. No, they don't think that. The opposing side thinks you're an idiot and a fucktard, and they can't figure out why the fuck you believe this shit. Who proved it to you? What diagram of a photon makes it make sense to you? How the hell does the photon know how to do all of this crap? It's an elemental piece of energy. How the hell does it have all of these functions? Who gave them all those functions? God?
Well, it's how we can explain its behavior.
Yes, it's easy to explain. I mean, frankly, if you just draw the damn thing, it gets really easy when you start realizing, oh, what's there in an experiment? You know, so let me go dissect the complicated, hard to explain experiment. Yes, let's do that. So what the hell do you have? Okay, there's a single slit. What do I have? I have an opening. Okay, now I know in light, this single slit, right, will produce a interference pattern. I mean, it's going to be exactly the same pattern, right, in the sense that it's going to have the double maxima. Okay, so it has all the features. It's all there. And they're going to call this a diffraction pattern. What are you diffracting with what? Okay, and then obviously, but some physicists are honest, and Professor Lewin says, yes, that's a ridiculous thing to say. I mean, obviously, this is the same phenomenon as the double slit. There's no difference in these phenomena. It's obviously the same mechanisms causing it. And the obvious answer is if I want more of this, okay, and less of this, I just make this slit smaller and smaller. I just make the surfaces smaller and smaller, meaning that it's more likely that every single photon will be right next to a surface. And then I'll get more and more of this, okay, and less of this. I mean, it's telling you, it's signaling the truth right to you, okay? And what you're certainly not going to see is that, oh no, there's a wave coming out of here. And then the wave comes out of here and it makes a interference. Oh, wait a minute, there's nothing to interfere with. How can I have interference? There's no two waves. And if I try to bisect this, you know, into some boob scenario, there's no rational reason why there's two waves coming out of the one opening. No rational reason whatsoever that you could explain why there'd be two sources, two wave centers. There's not two wave centers. It's just nonsense. The two sources, these are the two sources. These are where you draw your vectors from. You draw your vector from this surface. You draw your vector from this surface. That's the math that gets you the absolute correct answer. So why is there a discussion? This is easy to explain with particles. Okay, not hard to explain, easy to explain. I mean, draw your waves and show me how it makes mathematically sense with the single slit. It makes no sense at all. And then draw your waves with the double slit, right? Because then you got the problem of, you've got your you got your double slit, right? Okay, and you make a wave here, and you make a wave here. Well, that wouldn't make any sense, right? Because, well, if I do the math from the center of the wave, I'm not going to get the right answers. The only way I can get the right answers is I have to have this distance and this distance, and then this distance and this distance. This biggest distance will make the little dots. The smallest distance will make the envelope pattern. Absolute truth. Problem solved. It's all about the surfaces. The surfaces are the deciding mechanism in the experiment. It's a 2-surface experiment with a single slit. It's a 4-surface experiment with a double slit. That's the truth. The surfaces are causing the effect. This has nothing to do with anything called interference. Photons can't interfere with photons. That's why you can't shoot them at each other. You can't bang them into each other. Force doesn't interact with raw force. It has to interact with the catalyst of matter. It has to push matter to push force.
So I think
I love that.
I think that a lot of it can be explained as a wave, and in some cases you can explain the behavior as a particle, but you have to be careful not to think that it's actually a particle. Like,
no, you have to be careful to recognize it's actually a particle, and all of the wave nonsense is just a statement made by religious people. They're just claiming it waves. They have no evidence of a wave. It's not even in Maxwell's equations. There's no wave in Maxwell's equations.
a ball coming at you.
Okay.
All right, so here's another nut. Yeah, so it is a college full of, so I think this is the head nut, maybe. I'm not sure. He's got an interesting stack of books. So, or papers. I don't even know what that could be. Phone books? I don't know. Well, anyway, let's just play along.
And you're going to cut this so that I'm actually saying whatever you want me to be saying, right? You can put that on the floor. Or
Yeah, so he's also a paranoid kook.
anywhere.
That's right. So you can end up saying, hey, I think photons are dumb.
And you will say, I think photons are the greatest thing in the world.
Okay, so, what's your name?
My name
Okay, this part I gotta catch.
is David Norwood. I'm an
David Norwood. Norwood.
associate professor of physics at
Okay, associate professor of physics at Southwest Louisiana something or other.
Southeastern Louisiana
And
University.
you don't have to be formal.
Southeastern University, Louisiana University. So it's another university in Louisiana, which is funny, right? Oh, God. It really is a kook asylum. I always said that about being a kid there. Was it was so nice to get out of there, but it's crazy house. It's just full of crazy people. I don't think I met anybody sane in Louisiana. All right, I was 7 years old when we left, 6.5. So obviously, I probably didn't have a fully developed, well-constructed opinion, but it certainly was my impression.
I should look at you.
No, you look at me, whatever makes you comfortable. Yeah, look at me. So, is light a wave or particle? No, how about this? I know you think.
It's a wave.
Right.
Right. Yeah, so we all believe it. We all convinced each other. We all think it's a wave because it's just such a wonderful word, wave. Blah, 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 blah. And we're saving a couple of letters, particles, 6 letters. It's 2 more letters than we need. So, yes, let's go with wave.
Okay, so at what point did you say, hey, this whole photon thing's bogus?
Okay, so
So how could it possibly be bogus when it's clear that the evidence indicates that it clumps, okay, that it hits photographic paper and it either all or nothing. You either change the little dot of surface, you either oxidize it, ionize it, or you don't. You change its color, you don't. It's on, off. So in all these experiments, photodetector, this, that, they're all clump detectors. You can't can't detect a photon with anything other than a clump detector, indicating it's got to be pretty clumpy. And yet they say it's all a bogus conspiracy. Yeah, somebody made up this crazy idea. Oh man, it's pathetic. And I just don't get it. I'm sorry, this is like evolution, you know, versus a God theory. And you're just like, oh man, evolution is so much more sensible. It makes so much more sense. And you're saying, how could these scientists think this silly theory, this wooey, where there's these fields pulling on each other, they're moving everything in the universe, and they're all over, and but it all lands right here, but it was everywhere, and you know, everybody, it was there, and it just ended, but yeah, I went here, but it was everywhere. I mean, how does that crap make sense to you fuckers? Sorry, I just can't. I can't bear this because I can't understand it. I can't understand why these people want to believe this girly crap. I mean, it's so fucking silly. This is like nursery rhymes you tell a little kid or something. This is like, ew, it's like such a queer theory. I mean, it's just queer. Oh, the photon, it's got magical powers, it's got ESP, and it's got, I mean, it's just, ew. It's so creepy.
What's bogus is not the photon in and of itself. It's the way that you are taught the photon as an undergraduate in physics.
Okay.
Yeah, I'm not going to tell you really about how you're taught, but you're taught basically that it's a wavicle, and yeah, and that's silly. Except it's exactly right.
So I was taught what photons are, and here's what they are. They are infinitesimal particles.
So who says so? But okay, they're small, the little bits that make the photon. So this is the part that makes sense, right? The whole photon can't be infinitesimal. You have to understand, the whole photon can't be because the frequency is always proportional to the polarization. That's what you find with like microwaves and all these other things, because you can measure their polarization. You can use a filter, measure the polarization. You know exactly that it's rather large, as large as the wavelength. So therefore, light is doing the same thing. No reason to think it isn't. So the polarization is 500 nanometers across. How can something 500 nanometers across hit something 1,000,000 times? And it's more than 1,000,000. I mean, the electron is really 1,000,000,000 times smaller. But how can something that huge hit something 1,000,000,000 times smaller? How does that airplane land on a fly, right? How do I land a 747 on the back of a fly? Oh, that's right, I can't do that. That would be a ridiculous thing to believe.
That fly through space and sometimes act like waves and sometimes act like particles.
Okay, bullshit. So they don't ever act like a wave, in my opinion. I've never felt a photon, saw a photon, experienced it as a wave. I've never been able to look at a light bulb and say it's waving at me. Sorry. Nope.
Depends on their mood. No, I'm kidding. It depends on what you do, right? So the idea is if I measure something that...
So, okay, these are all these ambiguous statements about a measurement, and the only measurement there ever is make electricity, right? There's no other way to measure it is to make it cause electricity. Is there some other way for me to collect a photon than to make it make electricity? I don't think there is. Anyway, continue.
Depends on interference, then I'm asking if it's a wave, and it says I'm a wave.
So, you know, again, the interference argument can be made with radar experiments and radio experiments. So it's just a very simple argument. If I just change the experiment, instead of shooting through 2 slits, and I just turn it this way, and now I just send radio waves this way, I'll create exactly the same pattern, and I just move my detector antenna this way, and it will sense the same thing. On, off, on, off, on, off. Now, you won't have any central maxima, you know, that's twice as big, but you'll get an on-off pattern. And yes, it's just jamming. That's all you're doing. You're taking the same signal, and you're just hitting a point where when they're equal distant, you'll get twice the signal. When they're out of phase by 1/2, your receiver can't pick up either one. It can't tune into one or the other, because it doesn't look like the right frequency. Effectively, it's twice the frequency. It's a harmonic. But anyway, it basically is just called jamming. But that experiment basically proves nothing's interfering. There's no opportunity for the two radio signals to interfere with each other before they hit the surface. So they can't be interfering.
I ask it something about particle-like properties, and we can talk about what particle-like properties are. And
Yeah, unfortunately, he's not going to do any of that, so you're not going to talk about anything.
then it tells you that. And the problem is this notion of infinitesimal particles that fly through space like BBs and bounce off of things and act like BBs do, like classical particles do. Then
Yeah, right, and you can do that. It's just you've never tried. You've just concluded that it can't be done because somebody said it can't be done. But you never tried. You never drew it. Because it doesn't take that much time once you start drawing it to say, well, yeah, BBs at a frequency does make sense. That could send a signal from one object to another object. It's going to send the information. And it certainly would carry momentum. And photons carry momentum. So in so many ways, it makes perfectly good sense. You still transfer the information. The photon still has an individual character, green, blue, red. So you don't lose anything. So why is it a big, you can't do that? Why is there a, you can't do that prohibition?
you have a lot of trouble if you learn that as an undergraduate and then you go and get a PhD using building and designing lasers and using them for transport measurements. Then
so now he's arguing that somehow if you actually be a laser engineer, you're going to be convinced it's waves, when obviously the laser is one of the best pieces of evidence against wave theory.
You wind up trying really hard to try to make this weird model work, and it just doesn't work. And you.
So says you. So again, it's just this blanket statement. They never tried it. They never did any experiments to pull the truth out. They haven't even put, like I said, photographic plates on either side of the slit experiment. So if they would have put the photographic plates on either side of the experiment, they could see how much of that pattern actually goes in these wave directions. I mean, if it's a wave theory, then it has to really go 180 degrees. If it's a wave theory. All right. And so that would be a good piece of evidence. Never done the experiment. So, I mean, this is just such bullshit to claim they've proven it invalid when they never even thought about it.
Find out eventually that there's just no truth in it.
Says you.
It's not a good way to think about.
Yes, it is. It works really well. Solves a lot of the problems, and your own math, it's explicit that the surfaces are the correct geometry. The waves you're creating have to be emitted by the surfaces, and there's no, you can't draw that. You can't draw how the wave goes over the edge of the surface. You know, it would have to be on this side of the surface, and you can't draw that. There's no rational way to describe your wave in the location it needs to be in, which is right with its center on the surface.
How light and matter interact, or even what light is. And the big discussion, as far as I'm concerned, is not whether or not there is a quantum theory of radiation. There absolutely is.
Right. So the quantum part, like I said, you could almost argue that everybody's agreeing that, you know, if it's either a synthetic quantum or a real quantum. Now, obviously, I'd say you're in bigger trouble with your wave theory and describing a quantum wave. And it's really easy for a particle theory to talk about a quantum particle.
And everybody knows that. It's that it has the actual quantum theory of radiation just has nothing to do with what people are taught at the undergraduate level.
So I don't know, what are they taught at the undergraduate level? They're taught all of this bullshit about some sort of waving interference. So he's complaining that they're being taught his crappy, silly theory. It doesn't make any sense.
If we're going to teach it, let's teach it in a way that's at least partly right.
So they can't even say all right. So, you know, it's like they're so arrogant. They got the truth, and yet they're not even, they can't even say, oh yeah, it is the truth.
Back to school doesn't mean starting from scratch. At Purdue Global, the learning you have gained through experience you already...
Okay, so now for...
All right, So anyway, let's see if anybody said anything. All right, just the indecisiveness, whether it's a wave or a particle, is just pointing they probably don't look enough. Well, they should be able to prove it, right? I mean, that would be the simple argument. If it's so obviously a wave, well, then they should be able to do something to prove it to me. Show me something. They should really go back to particle model. They should go back to Newton and start over, because yes, they ruined physics, relativity, bent geodesic, gravity, and 1/2 mv squared, all bad ideas, and they all just ruined a perfectly sensible road. So physics was on this really sensible road, getting right to the truth of the idea that there's force and matter, and the force tells the matter where it's going to go, and the matter going pushes on the force. So, it's just about the interaction between force, the stuff moving the speed of light, and matter, the stuff not moving the speed of light. I mean, you can't make it much simpler than that, right? So it's Sisyphuses and boulders, right? So, I mean, it's too bad Newton didn't say that. It's too bad he didn't have, quite enough evidence to get there. But it's pretty close to what Fadio was arguing, obviously. Ultramundane particles, the force, okay, and then the more mundane matter. And that simple perceptual aid, okay, is so powerful. And they just threw it all away to go with this religious, wooey, wavy, magical, fluffy, girly crap. All right, the fact that this professor is just saying all this with no real evidence is shocking. It's just shocking how, I'm surprised that this is college physics. That surprises me. It almost makes you want not to drive across a bridge anywhere in America. You're saying, wow, this is how people are being taught? I mean, it's pretty bad. But, I guess obviously they're getting something right. But, a little bit scary. All right. Is light a wave or a particle? So we're doing the same thing again. Some more.
For a super quick and not complete overview of a ball in an infinite square well and what this has to do with the photoelectric effect. Okay, so suppose I have this ball.
An infinite square well. So why would you even bother with this idea? So, but whatever. Let's see where this goes.
Ball moving back and forth between these walls, and we call them infinite potentials, meaning that if you move to the left of that, the potential is infinity and it cannot even penetrate that, not even a little bit. So if the size of this gets really small, then our classical mechanics doesn't work to describe this. Instead, we have to use quantum mechanics.
All right, so whatever that means. So they're trying to say that somehow if you get to the Planck distance, there's some other distance you have to worry about, and there probably isn't. So it sounds like just a pile of crap, frankly. And why would there be any problem? So as long as you don't believe in singularities, there's no reason to believe that you can't always just have the distance and have the distance and have the distance.
And so quantum mechanics deals not with the trajectory of the ball, but it deals with the wave function. So the wave function is the symbol psi, capital Psi.
Yeah, and it doesn't mean a damn thing that's coherent or reasonable. So, I mean, and then have psi divided by psi is just hilarious down here. Well, that makes a hell of a lot of sense.
You can see it down here in the equation, that's the wave function.
Oh, psi.
Okay, and
times psi. Okay, yes. Well, I think that's psi squared, isn't it? I don't know. Well, who cares? I mean, it's just whatever this is, right? This is supposed to be all knowledge of everything about the experiment, and obviously we never have all knowledge, so why are we even bother talking about this silly equation?
the wave function must satisfy the following equation, which we call Schrodinger's equation. So you've probably heard that before. Schrodinger's cat, Schrodinger's equation, that's all the same thing.
No, it isn't. So that's even more ridiculous to say that Schrodinger's cat has anything to do with Schrodinger's equation, because they're completely different physics. One of the Schrodinger's cat was completely just to make fun of quantum mechanics.
Okay, so it's partial derivatives with time and space and all that cool stuff, and the V is the potential. So in the well, the potential is 0, and outside the well, the potential is infinity.
So I don't even know what the hell he's talking about. So it's an elastic collision with the wall, or what? And outside the wall is affinity? I don't even know what the hell is he talking about. Out here is affinity, or it doesn't make any sense. What the hell are you talking about?
And the other important thing is the probability density. This is just the complex conjugate of the wave function. And so you can get something that would tell you the probability of finding the particle at different positions. Okay, so there...
Right, and so who cares? The particle's always somewhere if it's a particle theory, so I don't even have to worry about this crap. So it's only because you are saying it's a wave that turns into a particle. And somehow you're saying it turns into a particle when you do this special thing, which is observe it. And how the fuck do you do this special thing called observing? I mean, how does the universe not observe it? And you do something special called observing. I mean, right now a bunch of energy is bouncing off of me and nobody's observing it, so to speak. Right? You could argue the camera is, but I'm blocking the camera, so it can't observe anymore. So nothing's observing it. Oh, is it still being affected just as if it was being observed? Yes. Is it behaving exactly the same? Yes. So how can it be unentangled by one observation? That is, somebody opens their eyes over there and now they're observing my shirt. And when the shirt wasn't being observed, somehow it was entangled. I mean, that's a ridiculous argument.
Is our infinite square well. I'm not going to solve the whole thing. So suppose you break that wave function psi into a space part, and this is in one dimension, a space part and a time part. Then you can come up with the following solution, and I'm skipping a whole bunch of steps here, a whole bunch, okay? And I get this following expression for the wave function, and it's the sine n pi x over n.
Yeah, whatever. So look at this crap. N squared, pi squared, h squared, 2ma squared. I mean, just pile of crap.
A and the exponential term with the time in there, and we have these discrete energy values.
Wow, look at the big surprise that the ball is in the center more than it's in the other two sides. Woo! Would have never guessed. I mean, obviously the part where it's going back and forth through the center means it has to be in the center more often. Duh.
It have to have in order to have the boundaries at x equals 0 and x equal a be 0 because it can't penetrate. So we get these quantized energy levels. And if you plotted probability density as a function...
If you actually did this experiment correctly, there's no way the probability density could be 0 at this point. There's just no way it could be 0. So that doesn't even make any sense. Alright, so now you're changing the speed of the ball, I guess. It has to be going insanely fast at these points for the probability to be that low. I don't know how it speeds up going through the center.
Of time, you get this picture. That's an animation, okay? Because it's a stationary state. But since the exponential term has that I in there, time goes away when you find the complement.
Yeah, so it's just vaguely resembling some sort of thing that's sort of mathematical and sort of something, but it's not really anything rigorous or meaningful. I'm just trying to make it look like it's mathematical and rigid when it's not. It's just mushy shit. So do a real experiment and do a real prediction and do something real. Let me see you do a real Schrodinger's equation.
Complex conjugate, and you get a stationary state. So if you put at any of these quantized energy levels, it just stays there, which is kind of cool and weird. Okay, but all of quantum mechanics is weird. Now
that's a good reason to get rid of it. If it seems weird, or you look at it, the longer you look at it, the weirder it gets. Well, then yes, it's time to throw that in the garbage. Weird is a waste of time.
Suppose I put in.
So look at this bullshit, made up bullshit.
Two energies, a superposition of energies, energy 1 and energy 2.
And they're superimposed.
The wave,
how? They obviously aren't superimposed. One of them's on one side and one of them's on the other side, and they're switching sides. So they're obviously not a superposition.
Probability density will oscillate back and forth just like this. And the frequency of oscillation depends on, here you go.
Sorry, this is just nonsense, bullshit. This is like a waste of everybody's time. Let's see if there's anything in the comments here. All right, they should really go back to the, let's see, the fact that the professor is just saying all this. Oh, okay, yeah, no, there is no new comment. Sorry. A little bit hopeful on my side. Yeah, I was hoping
Change
for
in energy,
distraction.
E2 minus E1 over H, where H is Planck's constant. This is that same thing. Most people say E of a photon is H times the frequency. Okay, so that's that same expression. But this just says the frequency of oscillation.
All right, so again, that whole idea that the energy of the photon, and it's not about energy, just like pointing an arrow makes an arrow more effective at breaking through hide on an animal and killing it. But it doesn't mean the arrow had more energy. And the fact is, having a smaller time between events, that is a higher frequency, does give a photon more capacity to affect a surface, but it doesn't mean it's carrying more absolute energy. It's just carrying it in a way that's more effective at causing disruption to atoms. It ionizes them, in other words.
Is proportional to the energy change. Now, if I want to get something to change energy levels and I apply this frequency of perturbation, if I jiggle the potential with that frequency, it can get it to change energy levels. Isn't that cool? And this is not
Whatever this is, right? This where we show any energy levels being changed. Where we showing anything?
crazy photon stuff. This is your basic undergraduate level quantum mechanics. You can see.
Yeah, it's just bullshit. That's all it is bullshit. It's a complete misunderstanding of the concept of energy and the idea that the only thing thermodynamically, okay, you can't make any more energy. And the fact that some configurations of motion will break things doesn't mean that configuration has more absolute energy. Everything is vulnerable to a different form of effect. So you could argue that a suit of armor is really good against a sword, really bad against a high velocity arrow, a high weight arrow, shot from above, especially. But every kind of, like I said, every kind of weapon or mechanism you could use has a vulnerability, a different vulnerability.
The perturbation stuff's a little tougher, but you can see this. And I'll include links to these simulations. I didn't make them down below.
I mean, I just can't wait because that simulation makes perfectly good sense. Wait, no, it doesn't.
Let's fuel up, Limu. Lots of people to tell about customizing and saving with Liberty Mutual. Oh, those are mine.
Drinking warm water with cinnamon before bed eliminates this parasite from the pancreas, restores blood sugar levels.
Yes, the parasite. I've never heard of. Yes, okay, thank you. These are YouTube ads. I mean, these are ads on YouTube videos for get rid of your parasites.
So what's the point here? What do we do about light? I think one of the main things is, I'm just going to keep flashing this on my face like that.
Yeah, it's very exciting.
I think one of the main things is that light's complicated. It's definitely not this stream of BBs get shot out of the light. And I think
I just say it's definitely not because I say so. I just don't get why that's a closed door. I mean, what exactly about what the frickin' thing is doing makes that a door you have to close? That's the part I don't get. Makes so much sense. The little BBs are hitting your surface. They're going to push on the electrons. The electron's going to push back. It's going to create BBs coming back at me. Why wouldn't I think this is just about a reaction, an interaction in a universe full of energy? The energy is in the universe. It's in the empty space flying between things. And your surface is either going to reflect it in one way, or it's going to reflect it in another way. It's going to absorb it. It's going to reflect it. It's going to do something to it. And I'm just going to see what your surface does to it that's different than what my surface will do to it. That's all. It's just we're just throwing it back and forth at each other. We're at equilibrium. We're not going to get hotter and hotter. So obviously the photons aren't making us hotter and hotter. The photons are just bouncing off of us. We're throwing them back and forth at each other.
That's the biggest problem. The way it's presented in textbooks, it's really leads students to believe that it's easy.
Amazing. So I don't remember where you read anything in the textbooks that were telling the students to believe in particle theory. So I don't recall that part.
Either a wave or it's BBs, and it is never BBs.
Okay, it's always BBs. And there's just no experiment that can't be perfectly explained by BB theory. And there's lots of experiments that can't be explained by wave theory. And I'd argue the two-slit is the obvious one. Because the fact is, let me just draw it one more time. I mean, if you do the Young theory, okay, of how this is supposed to work, you can see it dramatically doesn't work. It can't work. It's bullshit. All right, and the simple idea is if they did it, see, they don't do real double slit experiments, right? Whenever they detail a double slit experiment, they always say infinitesimally small slits. Why do I have to make infinitesimally small slits? That's silly. Why would I make a slit infinitesimally small if I don't have to? So really, yes, so the truth is I can do the experiment with any size slit. All right, and the fact is the bigger the slits, the more pattern I'm going to get. And the simple truth is, if I do the Young diagram, right? So if you do this silly thing, right? All right, two waves, and here's their centers. So you have two waves coming out, and I'm going to draw all these stupid lines, and I'm going to say these are interfering with this, and this one's going to interfere with that one, blah, 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 blah. Well, I should have gone here with that one. Right? Well, where's my centers? Oh, here's my centers, here. And the absolute truth is, if I use those centers to do my vectors, I will not accurately predict the location of the ons and offs. I'll get the wrong answer. Because the only one that's going to give me a right answer is either this widest distance, that is, I take the distance from here and the distance from here, or I take the distance from here and I take the distance from here, that kind of thing. But that's it. Those are the only things that could give me right answers. And obviously, in the case of the double slit, those two things have to line up. All four sources have to be in phase. They all have to be a wavelength, at least one wavelength, longer. So this one would be one wavelength, this would be two wavelengths, this might be 5 wavelengths. But they all be whole wavelengths longer, and then this spot will be the brightest it can be. And that's how it actually works. So, I mean, Young's own drawing proves that it doesn't apply to photons, because the source of your vectors that will get the right answer isn't in the center of the wave. It's on the surfaces. And obviously you wouldn't draw a wave here. Okay, and you wouldn't draw a wave here. And you wouldn't draw a wave here. And you wouldn't draw a wave here. And those are the actual ones that get the right answer. And again, it also proves that all four surfaces are involved, because if you really look at the pattern, it's a complex pattern. Okay, and it really does show you that the outside distance will decide how many of these little dots you have, and the smallest distance will decide how many of this envelope pattern is. So it's all perfect, solved, complete. Particle theory works. Wave theory, not so much.
Never little tiny particles that get shot out like that. Yes, light is complicated. There is a quantum theory of radiation.
And it doesn't make any sense. And again, to fake it, you have to say, make those slits infinitesimally small. And what does that turn it into? So instead of being the 4-source experiment, right, the 4-surface experiment, they turn it back into the 2-surface experiment. Because 2 of the surfaces are so close, they're the same, right? If I put two headlights right next to each other, I can't see it as two headlights anymore. Same thing happening in the way they cheat the analysis. And they're just cheating it. They're just saying, we have to turn the double slit into the single slit again because we can't explain that envelope pattern. We can't explain the two patterns. So we have to get rid of the two patterns. That's their physics. Cowardly nonsense.
The photoelectric effect is cool, but you don't need this photon idea.
Yeah, you do. Because it doesn't make any sense to say this spread out wave goes everywhere and then it decides to just go to one place and then it retracts all the energy that was going to all the other places. Somehow it retracts it all and puts it right over there. That is an idiotic description of reality.
In there. And really, I think that might be the biggest thing. Why is the photoelectric effect in these introductory books? Is it cool? Yeah.
So amazing that he's basically saying that a piece of glaring, reasonable evidence that shows a huge flaw in wave theory should be extracted from the argument. Amazing. When it's perfectly valid, it should just be ignored. Because there is no way to explain it with waves. So again, he won't do that. He's not going to give us the wave theory of the photoelectric effect.
Yeah, it's cool. Is it historically significant? Yeah, it's pretty significant. But I don't think it really leads to this broader idea that students need to understand about physics. I think it's more important to focus on the fundamental things. In quantum mechanics, we can explain the photoelectric effect. So
I don't know where you do that though. As a wave theory, no, you don't. You don't solve it as a wave theory.
I think we just, I think it also says, look, here's a textbook. Things get in there, and they kind of get stuck in there. We kind of, why do I know about the photoelectric?
So it's just so funny how he's talking about things getting stuck, and that's the whole point. Leibniz just made up this idea of mv squared. There was no experimental evidence. And then de Châtelet shows up, and his Granzfeld guy who believed in perpetual motion does some clay experiments and badly thought out that can't possibly get to right answers, and everybody falls for that. But a modern physicist should be able to know, you can't use that. I mean, you can't dent a surface with an uneven surface, a round surface, a constantly changing surface. You can't dent a surface with that and expect that it's going to reveal energy levels, because that's like putting a point on an arrow and saying it gave the arrow more energy. It can't give the energy. You can't give it more energy.
Photoelectric effect. It's because it was in a textbook. And then that's why I teach it. I teach it the way it was. And then that kind of sticks in there. It's really weird. We really need to think about what we do.
I wonder why a lot of these colleges don't have videos of their lectures. I'd like to see one of his actual lectures.
But that's true for everything, right? But in the end, I also like to think about Pluto. Is Pluto a planet or a dwarf planet? Who cares? Pluto's awesome.
Oh yeah, what's the whole idea of arguing the question? But I'd say obviously anything that has something orbiting it, you really have to call it a planet. I mean, even if it was a baseball and it had a pea orbiting it, it'd be so cool that you have to say, yeah, that's pretty cool. We'll call that a planet.
Okay, and I think the same thing's true with light. Light is awesome, and then we can do some really cool things. Okay, so this video is a little bit different than my other videos. I kind of interviewed.
There's obviously a real. You really need a mass, right? So the problem with my analogy, let's say if I took a cannonball up into space, all right, something really dense and heavy. There's a minimum weight it has to be able to have a pea orbit it, right? So yeah, you really have to figure that out. But we should be able to synthetically make such an object. But it really does have to have a minimum mass that has to be pretty substantial. I mean, it'd have to be probably a lot bigger than a cannonball.
some people and made it a little bit longer and edited it, which I don't normally do. So if you liked it, let me know. I can make...
Yeah, it'd be nice if you could make actual interaction videos where somebody proposes some arguments and you answer those arguments. So I could make arguments about how levers work and how pulleys work, how they conserve momentum, they don't conserve kinetic energy. All right, now I talk about ballistic pendulums and how, yeah, all the kinetic energy disappears in the most extreme bullet example. 99.94% of the kinetic energy is missing, and nobody sticks a thermometer in the pendulum to prove it's there. They don't even take one. You do a lot of thermal experiments. Well, why don't you show us with your thermal camera that there's 2,000 joules of heat in the pendulum? But there's all these experiments that basically demonstrate that this idiotic v-squared concept isn't real. It can't be collected. You can't even use it in space to navigate. You can't even use it to, land on the moon with a lunar module. If you use kinetic energy and calculate your thrust in joules, you'll get a wrong answer and you won't land on the moon. Fact. If you calculate it in momentum, you'll get the right answer. You'll figure out that you get an equal and opposite reaction because kinetic energy doesn't work, doesn't obey Newton's third law. I mean, all of these things should be answered by one of you physicists, and you've all run away. Every single one. And such. So anyway, so this is an interesting guy. I mean, he has had this channel for like 20 years. He's got his whole life kind of documented there, so he's had kids and all kinds of stuff, and it is sort of interesting. And he's probably about, he's getting close to 60 now, I guess. I'm guessing from some of his other videos, and the age he was, so something like that. But anyway, no, human beings are interesting. So look at the regular phone back there. It's an old-fashioned regular phone, huh? Interesting. Who has one of those? I mean, I have a, one of these kind of phones. Because it makes some sense to have these kind of phones, one of these, old phones. But yeah, well, I actually have a regular old phone too, so I shouldn't say anything. I don't have a. It's not a landline anymore. So I have a VOP thing, a VOP, whatever it is. Well, anyway. It's none of your business, so I shouldn't even be telling you that. So never mind. Is there anything else? Oh, I'll see if anybody else got anything to say. I guess I got to play another video. Let's see. Sorry, I'm quite tired today. Understand. Let's see. Are these equations supposed to be coherent somehow to reality? Will there be any evidence? No. So that's the real problem, right? They always talk about it. I've never seen anyone ever take a circumstance, like a pinball machine, and then take the Schrodinger equation and solve something. No, never seen it done. Okay, let's see, somehow. The YouTube ads annoy me. If anything, the commercials do the opposite of their intentions. Well, they scare the hell out of me that this stuff, number one, you can actually convince people to, it's almost like, eating rhinoceros penis or something. It's like they could actually have a commercial where somebody's selling rhinoceros penis as a cure for something, and they could actually get people to buy it. I mean, this is how it's so ridiculously bad that you're saying, who could possibly be convinced by these commercials? And you're saying, shouldn't it even be illegal to steal money from people that dumb? I mean, it's disgraceful. It's just, it's disgraceful that these commercials exist, especially the ones that start with fart noises and shit. You're just saying they're so vulgar. I mean, what kind of moron could find that an acceptable commercial break? I farted. It's Beavis and Butthead. It's so goddamn stupid that you say, no, nobody could find that at all compelling or interesting to be farted at in the middle of their movie. I don't understand quantum mechanics and their equations. Yeah, well, that's to say the least. There's nothing to understand because they never do the equations. They just pretend it's the most proven, wonderful theory ever. It predicted everything. Every single thing. It's been predicted by this wonderful predicting theory that predicted everything. Yeah, sure. Yeah. All right, well, let's do one more. So, what's a beam splitter? So this ought to be pretty funny. You know, so it's at least it's still photons.
We're going to talk about laser pointers and beam splitters. So here's a laser pointer. You can get these really cheap.
Fix the volume again.
Shine it right there. But what if I want to make a dot over here and there at the same time? I want to make 2 laser beams. That's where you need a beam splitter. Well, one thing I could do is take a mirror. So this is just a plastic mirror, and if I shine this, I see that I get 2 beams. In fact, I have some professional fog here.
So it's really not 2 beams, right? It's not what you need a beam splitter to do, so that's kind of a silly argument. It's just 1 beam reflected.
You can see that, so you can see the beam, okay? And I can turn that. It's kind of fun to play with, especially when you see the beam. Okay, but that only gives 1 beam. So here is a beam splitter. This is a plastic box.
All right, and it could be a glass slide. So that's what I used years ago, okay, in doing some of these interferometer type experiments. And the realization was, why do people talk about beam splitters? Because a plain piece of glass will create a beam splitter. A 50-50 beam splitter, frankly. So why do I need a mirrored piece of glass? You know, and it's a real question. Why do I need the mirrored piece of glass? Partially mirrored. And then you say, oh, you know why? It's because it's going to put a bunch more, and it really all does have to do with the double slit experiment. That's the funny, ironic part. The answer is because of the double slit experiment. That's the solution that explains. It's the same exact phenomenon, frankly. So all the beam splitter's doing, okay, is this. And you found out, like I said, when it's, you know, the more you do the experiment, the more you play with this at an angle. Okay, so you're taking a piece of glass at an angle. And the trick is if you blew moisture on it, okay, you can understand, you'd end up creating, like, say if I was to draw what you would do. Okay, so you have moisture. What's moisture going to look like on the slide? It's going to look like a little bubbles. And what do those little bubbles have? Oh, they all have surfaces, right? So it's a diffraction gradient. So the more moisture is on the slide, the more diffraction. And so what you're really doing, right, is when you shine your laser at this angle, is half the light's going to go through, okay, and half the light's going to reflect. And so you've accomplished the beam splitting. But the trick is the light that's reflecting didn't go through the grating. So the light that's reflecting didn't go by a surface. So it's not diffracted. It's not spread. It's not creating fringes. So this light, no fringes. This light did go through the little surfaces. It is getting diffracted, okay, and it is spreading. So it has elements that are spreading. So when they put it through the experiment, now they're going to bounce it through a bunch of mirrors, blah, 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 and then it's going to come back again. One beam is going to be spreading the whole time. So it goes through all these mirrors, bang, 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 and it's spreading the whole time. And the other beam isn't spreading. It's staying a little beam. And so that's the difference. Then when they come back, this one is now going to do the spreading. So it's going to spread a little bit. But this one's going to come back and it's already spread. It's going to, you know, it's not going to be spread now, but it's already gigantic. And those are the 2 beams you're really combining. So you're really measuring how much the beam spread. You're not measuring how the phase of the photons. So it's not measuring the phase of the photons, it's measuring the width, the amount of spread of the diffracted beam. And then you're going to compare the 2 spread beams. And you'll find that one of them is spread 1,000,000 times more than the other one. Okay, because one of them spread through the whole experiment, and the other one only spread for the last little inch, or 10 inches. But anyway, so, this is the big joke, is that they don't even know how beam splitters work. You can buy a half-silvered mirror. Why would I buy a half-silvered mirror if I already know half the light's going to reflect off the surface? Why would I do that? Exactly, I wouldn't.
And I'm going to use this as a beam splitter. So let me show you how it works. I'm going to put it down right there. I'm going to spray some spray. And there you go.
So spraying the spray probably did make it work even better, but anyway. So yeah, see, the beams are almost, they're not the same, right? The one going through is a little brighter, but if he increases the angle, he'll get, he can make more and more light reflect. So it's just about increasing angles.
This beam, you can't see it very well, but there is a beam right there.
See, it doesn't look like a 45-degree angle because that looks like a 30-degree angle. So if he makes this a better angle, so it's 45 degrees and the light hits here, he'll probably end up with a equally bright spot.
So one of the beams comes in and goes through, the other one reflects off and goes.
And they have this assumption that those two beams are doing exactly the same thing. So that's the assumption of the beam splitter. So even though one of them is going through the diffraction gradient, and one of them isn't. And they can't figure out that, that probably means those two beams are different. They're not the same.
That way. So how does that work? Well, if you look at this plastic sheet or glass or anything like that, light goes through it and you can see through it. But if you turn it at an angle, it looks like it's reflecting. It's like a mirror. So at high angles, you get more light reflecting. Some comes, even at straight on, but at an angle.
Right, so even straight on it's 5 or 6%, and then it just gets higher and higher the more you angle it.
Some go straight through and some reflects, so you get a beam.
But you won't get the circular fringe pattern unless you do something to that surface to make it dirty. Moisture or dirt. So without dust, you can put dust on it, any way to put little particles on the surface, then you get the nice ringed pattern. But if you don't do that, you make it perfectly clean, then you won't be able to see the diffraction pattern because you basically eliminated the diffraction gradient. You took away the silvering, so to speak.
Splitter. Let's see if I can do right there.
See, when he sprayed whatever he sprayed, that put a bunch of droplets on there. So he really should be able to do, if he had mirrors, he should be able to shoot these things back in again and get a nice fringe pattern.
There we go. Cool.
Like I said, I did this on my porch. I used bean cans and mirrors, and and it really was an interesting reveal that all this talk about what a beam splitter is, and it really just doesn't make any sense because they're using prisms and using all kinds of devices, and you're saying, well, why are they doing any of that when this works?
Is that not cool? Yes, it is. You can do a better beam splitter with better glass, but that's what it is, a beam splitter.
So it would have been better if he did the whole interferometer thing, but he didn't, so can't show you that. Would have liked to, but I can't. Alright, so that was a quickie. So I guess I might have one more here. Might as well play, I guess. Alright, yeah, I haven't seen this one yet. So it's called Intro to the Momentum Principle, whatever the fuck that could be. So I have no clue. And so we'll see what it is.
Here I have a ball. And if I let go of that ball, it falls. And I gotta pick it up. So, in the beginning, people said, what's going on with that falling ball?
Sorry,
and
I didn't have the
there was a
video
great guy, and his name was
My bad.
Aristotle. And Aristotle says, well, the ball's falling, so something makes it fall. And if you push on something.
Okay. So, yeah, we don't need to go back all the way to Aristotle. Obviously, that's just be a little bit too silly of us. So I guess I'll do this real quick in case it wasn't shown in the video. So that's what he did. So he shines the laser, it reflects, there's a spot on both sides, so we now split the beam into two different beams. And again, you can see that this degrees is not quite the 45 degrees, and if you did 45 degrees, this bright spot would be probably almost as bright as this one, and you'd get a more equal pattern. But the fact is you get two beams. You split it into two different beams, but they are in fact different. One of them has been affected more than the other one, has properties that are different. The two beams don't have the same properties because one of them did reflect off the surface and one of them penetrated the surface, and those are two different things and such and so forth and whatnot.
Like the ball, or if you push on it sideways, this is a better example. Actually, if you push on it sideways with a constant force, it's going to move at a constant speed. The harder you push, the faster it goes. And that
right, twice the force, twice the motion, 3 times the force, 3 times the motion, not, as Leibniz would say, 3 times the force, 9 times the motion, or 9 times the force and 3 times the motion, or whatever the fuck it is.
That all made sense, and everyone said, yes, Aristotle's so cool.
So again, the fact is that Aristotle in that sense was right, that obviously the world does work by force pushing objects, and it's happening all around us. That's thermodynamics. All energy is the same energy. It's all motion. And you can move atoms, you can move electrons, you can move protons, you can move ducks, you can move bricks, you can move all kinds of different objects. And it's just about mass and motion. And the force is energy that isn't pushing anything. When it's pushing something, it's captured energy, it's working, and when it's free, it's free.
And Aristotle was wrong.
So whatever.
And it turns out that forces don't make things move.
So again, it's just such a bold statement that won't come with any evidence. There's absolutely no reason for somebody to think forces don't make something move, and that things moving the speed of force move things. The speed of force is gravity, the speed of force is magnetism, the speed of force is electricity, the speed of force is light. And all those things move things.
Forces change the motion.
No, same difference. Now, how exactly is it a difference? Yeah, there's no difference.
Change is the key word there.
No, there's no key word there.
And that's where we get to the momentum principle. What do forces do when the net force is not zero? We've already looked at
right, so again,
what happens.
This mush about what a net force is, it doesn't matter. All you have to have is a different force. Two things can't collide into each other unless there's something about them that's different. So nothing can happen until something has a vector that's different than some other vector.
When the net force is zero vector, but now what happens when it's not? So the first thing we need to consider is the idea of momentum. So we can define momentum. Momentum is the product of mass and velocity. And velocity is a vector.
So momentum is force, it is weight, it is pressure, it is energy, it is, what else is there? Heat. It's all the same thing. Just masses moving. You can either have really big masses moving of velocity or little tiny masses moving of velocity, but that's all you can have in the universe is masses and velocities. And photons have mass and they have a velocity.
Vector, and mass is a scalar, so when you multiply those together, you get a vector.
So we vector scalar crap, we don't need to even know anything about this nonsense. There's no such thing as a negative motion. You can only have positive motion.
So momentum is a vector. And this is what changes when you exert a force, a net force on something. So let me just go ahead and write out the momentum principle, and then we can talk about how it works.
Yeah, well, there's no such principle I've heard of.
F net delta P over delta T.
Right, so delta T, right. So that's Newton's formula. And again, the time part isn't a net part. So this is where they got it wrong again. This isn't what Newton said. Okay, the net force, you don't need, it doesn't matter what the time is. Time is irrelevant. You're talking about a net force. And so the change in your momentum will be exactly what the force is. That's it. Time won't make any difference. It's 1 unit, the net unit. So it just doesn't make any sense to say the net force when you're going to have something that keeps happening in units of time. That wouldn't make any sense, would it? No, it makes no sense at all. So time has to be a 1. So there's no point in doing this fraction. There's no number in front of the t except 1 if it's a net force. There's just the total amount of time. And there's only one total. It can't be a 2. It can't be a 5. It can't be any other number than the net amount of time. So it's irrelevant. It's in 1 unit of time.
That's the momentum principle. It says that a net force changes momentum with respect to time.
Respect to what time? No, it doesn't. The net is the net. It could be 6 years. It could be 500 years. Doesn't matter what it is. It's the net.
It's very useful.
It's pointless.
Very powerful.
And it was only used to describe a gravitational equation where it comes in units, and that wouldn't be a net force then. The net force wouldn't be coming in, you have to calculate the units of time. So it wouldn't be the net force, it'd be the force per unit of time. So if you want the fraction, if you want 9.8 meters per 1 second, then you write this formula. If you don't want 9.8 meters per 1 second and you want the total force and the total effect, then you just don't bother with the time.
So let's just look at a quick example. Let's say I have this ball. And actually, to make it not completely trivial, this ball is moving along at 1 meter per second, and I push on it. It's moving this way, but I push this way for 1 second. Everything's 1, okay? Except for the mass of the ball. It's 0.1, 100 grams. Okay, so here I have the ball, P1, and then I push on it this way.
Right, so you know perpendicular isn't going to make any difference, so it's not going to change anything that matters. So, you know, this isn't terribly interesting. I don't know how this is a momentum principle. The two motions don't. Let's see what's the right way to say it. All right, well, I'll just wait for him to say what he's going to say. But obviously they'll be converted into an object moving in a new direction. And the object's not going to have twice the energy or anything like that. You can't add the vectors directly. You have to add the vectors as a hypotenuse. So maybe he's just going to show vector math. Maybe he's calling vector math the momentum principle. I don't know. I'm trying to find out where the momentum principle comes from in here.
This is my only force acting on it, F net. And then so what's going to happen is the ball is going to be going like that, P2. And I want to find that final momentum vector. So let's just use the momentum principle and solve this for P2. So I'm going to say equals P2 minus P1 over delta T. That's the same thing as change momentum. I can multiply both sides of this equation by delta T and I get F net delta T equals P2 minus P1. Yes, these are vectors, don't forget. Now I can add P1 to both sides and I get the following. P2, P1 plus F net delta T. So now I can find P1, I can find F net. These are all given. I can use that to...
So yeah, given by what? So again, that's just sort of bullshit. So you said you're going to push on it with some force for 1 second, but it has to be... I guess that's what... I don't see how that could be force net, but go ahead. All right, fine. I don't know what... I mean, it should just be force, not force net.
Find P2. So let's just pick some values here. Let's say the mass is 0.1 kilograms. V1 is 100 meters per second. F net equals 0.10 newtons, and delta t equals 1 second. So now I can just put in my values here, and I get P2 equals P1. P1 is going to be equal to mass times velocity, so that's going to be 0.1 times 1 is 1. The units for momentum are in.
This isn't going to make any sense because somewhere in here he has to do his Pythagorean thing. He has to find his angle. So I don't know how he's exactly getting away with this.
Kilogram meters per second. And yeah, there are no special units for that other than that. I know it's weird. But. Okay, so P1 is going to be equal to 0.100 kilogram meters per second. And then F net times dt is going to be 1 times 0, 1 times 1, 1 times 0. So it's going to be, but you'll notice here I get Newton seconds. And a Newton is a kilogram meter per second squared, so Newton
So a silly second squared. There's no second squared.
seconds is a kilogram meter per second. Same units. So I get plus 0.10
No such thing.
vector kilogram meters per second. Now I can add these two. I get 0.1 plus 0 is, yeah, I know, it's easy. Okay, it's 0.1. So it's going to be 0.1, 0 plus 1 is 1, 0 kilogram meters per second. So that's my final momentum. Now what if I want...
Yeah, convert that into something real, please. So what does that say? It says absolutely nothing. I mean, do you see how that says absolutely nothing? He's saying it's going one this way and it's going one that way, when it's not doing that, right? Because it's going one this way. So he still has to do the, side squared times side, times side squared equals hypotenuse.
To find the final velocity, then I'd have to divide by the mass. So if I divide this by the mass of 0.1, I get 1, and then that's going to be, what, 10? Is that right? 10? Yeah, 10, 0. I won't write it out because I'm running out of room. But that's your basic introduction to the momentum principle.
So that made no sense at all. So he never even finished that equation. Frankly, it didn't make any sense out of that at all. I mean, he really is, you got to say, this is pretty sloppy science.
Okay, now some other important things. Some people may say, hey, but what about Newton's second law, right? What about that? Same thing. Okay, I'm going to show you, for the most part, it's the same thing. It's not completely the same thing, but for the most part it is.
Does that make even any sense? No. So he didn't even solve it here. That's not a solution. He didn't tell us how fast it's going in the new direction. So he didn't tell us anything.
Okay, let's say I'm going to erase this and start over. But you did notice...
I mean, to add the vectors, you have to do the vector math, which is just the Pythagorean theory. You're just taking two sides, and you're saying that's a right angle. The two sides are perpendicular in his example, and you're getting a hypotenuse.
There's two things in that problem I just erased. One, it changed directions. You can do that. Two, it actually changed magnitude too, because it didn't change the magnitude of the speed in the x direction, but it did in the y direction, so the total was different. Okay.
And you never did the total, though. That's the whole point. It's not in your answer.
These are vectors. That's important to realize. And this is the net force. Okay, I'm going to put...
So again, it doesn't even mean anything, the net force being applied. It's the total force being applied.
In my definition of change in for momentum here and say delta mv over delta t. Now, in the special cases where the mass doesn't change, I can factor that mass out of the change and I get m delta v over delta t. And we remember from before that the definition of average acceleration was a change in velocity with respect to time. So this is ma. Okay, so that's Newton's second law. It says
No, it's really not Newton's second law. So again, just lie some more. Newton's second law is basically force equals momentum. The change in the momentum is the amount of the force. And the force is the amount that changed in the momentum was changed. That's Newton's second law. Twice the force, twice the motion, 3 times the force, 3 times the motion. They keep trying to turn it into something else. And it wasn't something else. It's just a lie. I mean, I don't know how many times you have to see this over and over again where they say Newton said this and Newton didn't say that. It's not what he wrote. It's not how he calculated it. It's not how he understood it.
F net equals ma. It's essentially the same thing, except that it's not. There are cases.
So Newton would write F net equals the net change in your momentum, period. Force is the change in your momentum.
And we'll use this sometimes because it makes things easier. But this is actually more fundamental because this.
Yes, exactly. That's the one that's actually accurate, closer to what Newton wrote.
This includes cases where the mass is not constant. This includes cases where the definition of momentum doesn't work. And in fact, if you go really, 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 really fast, like rocket, spaceship fast, then there's a better definition for momentum. And this works.
Says you.
This doesn't work. Okay, anything else about momentum? That's super quick. But once we find the change in momentum, we can find the change in velocity. We can find a whole bunch of other things. Let me say one more thing, because I already wrote it down. The momentum update formula. I already solved for this. But here, remember this? P2, P1, plus F net, delta T. That looks a lot like the position, the velocity update formula. Let me do that. Actually, yeah. Wait, that is the velocity update formula. That's the same thing as the velocity update formula if the force changes. And then we could use that with the position update formula plus the velocity, which is going to be actually P2 over m delta t. And then T2 equals T1 plus dt delta t. So this is what we use in our numerical calculations.
Oh, whatever. I don't see how any of that gets you the right answer. So good luck. All right, that was kind of a waste of time, have to admit.
If the force, and this actually doesn't even matter if the force is constant or not, because we're going to do that.
Yeah, well, again, it doesn't. There's no such thing as this, net force. And when there's just either you're going to calculate the total force, or you're going to calculate a continuing force at a rate. Those are the only two things you can have: a rate or a total. And such.
We did it before using acceleration. It's the same thing. It's just a different way of viewing that picture. Okay, that's enough for the momentum principle for now because it's over 8 minutes and that's a little too long for me.
Yeah, whatever. 8 minutes. All right, Gary looking missed off again. LOL. I don't know what that means, but fine. Sick and tired is what I am. And this guy's a physics professor. Yes. Wow, what a statement. Force doesn't move matter. Yeah, it is quite a statement. All right, so I guess that's it. All right, so I guess I will toddle off and such. And so forth and whatnot. Yeah, that's enough. So, till the next time and such. Yeah, that's enough. I gotta hit this button.